Hello, it's Keith here, and this is lesson 26 of the simple series of my 650 assembly programming tutorials. Now, we've been looking at sprite clipping on a variety of different systems recently, and today we're going to be looking at the NES. Now, we're not quite looking at sprites this time. We're going to be, like I've done in the past, drawing our Chibiko graphic. That's the character you can see on the example over there and up there. We're going to be drawing that using the tile map. So we're going to be creating a grid of 8x8 blocks on the tile map that represents our character. We've got it set up so that the joystick is going to move the character around. I'm using my cursor keys here, but we can move the character around. Now you can see it's moving a little bit slowly and flickering a bit, and I'll explain why that is at the moment. But the important thing is when our character goes partially off the screen, the graphic is indeed clipped, and that allows the sprite to be partially on and partially off the screen. As I say, it's not a true sprite, it's actually using the tile map. Now we'll be looking at next time using hardware sprites, but I always like to do a simple example just using the tile map because I think it's a lot easier to get started with the tile map because you don't have to worry about things like having limitations on the amount of objects you can have on screen and working out which sprite you've got to use next in your hardware sprites. Now, first of all, I want to discuss the concept of logical units. That's the coordinate system I'm using in my mathematics today, and that will explain why when we move, our character's moving very slowly, but it's flickering very fast. So let's go over to our theatre screen. Let's have a look at this screenshot here. Okay, so here is the screenshot which I've used to represent the logical units of my screen. Now, when we're writing these sprite clipping examples, what we're trying to do is we're trying to kind of make all of our systems work in the same way, irrespective of the physical resolution of the screen and the capabilities of the system. And so in this case, we're working with tiles, which can only be in 8x8 blocks and on 8x8 aligned coordinates. But on other systems, we may have higher resolutions. And what I also wanted to do is I wanted to make the X and Y coordinates that our system used work within a single byte, because a lot of our systems are only 8-bit, including of course the NES. So what I've come up with is a logical unit system which allows a visible screen in the center of the logical screen, but then outside of the logical screen in this sort of dark area here, these are invisible areas, and this allows our sprite to be given an XY coordinate which allows it to be partially on screen and partially off screen. So for example, this position here, this part of the Chibiko bitmap, this sort of bottom area here is off the screen and won't be drawn. This light area here will be drawn, and basically the range of coordinates is of course 0 to 0, 0 to 255, 255, but the logical screen will be the area 64, 80 to 192 by 176, and this is effectively assuming we're working with a 256 by 192 pixel screen. And what we're doing is we're defining our logical units as being one logical unit is 2 pixels. So 2 by 2 pixels is 1 by 1 logical unit. Now on this system we're working in tiles, and a tile is 8 by 8 pixels, and so each tile is 4 by 4 logical units. And that means when we're drawing our Chibiko here, the Chibiko needs to move 4 logical units before it will move 1 visible tile, and that's why you're seeing it flicker and you're not seeing it move as often as you would expect. So that's how our code is working. As I say, we're converting logical units, in this case for tiles, but next time we'll use sprites where we can move in pixel precision. Now the other tricky thing with this example, and we've looked at it before, is the fact that on the NES we cannot transfer data to VRAM outside of VBlank. So what we're going to be using is we're going to be using the same caching code that I used in the YQuest example. We're going to look at it again, we're going to discuss how we're doing it. We've got a cache of changes that need to be made during VBlank, and we can only update a total of 32 tiles during each VBlank cycle in the way that this code has been configured. Okay, so we've got a lot to discuss, but unfortunately I think the first thing we need to discuss is the concept of how we're actually going to crop our sprite. So if we go over to our blackboard, we can have a look at this. Okay, so here's our blackboard, and what we're going to be imagining is that we've got a screen here, and we are going to have a sprite on that screen. And of course our sprite in this case is actually going to be a grid of tiles. So let's imagine it's just 4 tiles there. Let's imagine that that's actually vaguely well drawn and not a horrendous scribble, which it is. But anyway, artistic incapability aside, our sprite is going to move around the screen, and we're going to have to deal with cropping it when it goes partially off the screen. So for example, if it goes off the screen in the horizontal axis at the top here, well, what we're going to need to do is we're going to need to remove part of the sprite up here, and we're going to need to change the height of the sprite. Now, if it goes over the side though, we're going to need to do something different, but of course in this case we're working in 8x8 tiles, so we're always going to need to work and make sure we're working not in half tiles because that's impossible. We're going to have to work in whole tile blocks. So we're going to have to, if our sprite would be partially off screen, either bump it down or bump it up so it's in an entire tile unit on the screen. In the same way, if we're on the left hand side of the screen, we're going to have to change the width of our object, and we're going to have to change the starting position, and after each tile we're going to have to skip the number of tiles before the next line is drawn. So we would only be drawing a 1x2 area here on the left hand side of the screen. On the right hand side of the screen we're going to have to do something pretty similar. We're going to have to change the width to this area here, and we're going to have to skip this area here, and at the bottom of the screen we're going to have to change the height of our tile map to this area here as we draw it onto the screen. So it's going to be a little bit tricky depending on the position of our tile map graphic. We're going to have to adjust it accordingly, and we're going to have to discuss all of that in our code. So a lot of problems. Anyway, let's go over to our code and let's take a look. Okay, so here's our code. Okay, so we've got a lot to discuss, and the first thing we're going to discuss is the fill area with tile code. Now, I'm not going to discuss how to transfer patterns to VRAM. We've done all that before many times, and I'm not going to discuss it again. We're also not going to discuss how to read in the joystick, because again, we've done that many times before. The first thing we're going to be discussing is this draw player routine, which initializes the size and position of our tile map graphic for the cropping routine we're going to be using today. So we're storing the X position in 0 page entry B, the Y position in 0 page entry C, the width in logical units in 0 page entry H. It's 48 pixels wide, so that's 24 logical units, and the height is also 24, and that's being stored in 0 page entry L. Now we're storing the first tile number of the graphic we're showing. Our Chibiko graphic starts at tile number 128, and all of the tiles are consecutive in that pattern. We're then going to use a function called doCrop, which is going to handle the problem of cropping our graphic when it goes off the screen. So we're going to have a look at that first. And one thing that's important to notice is if the tile map object is completely off the screen, then we're going to set the carry, and we're going to just return without drawing anything. So we've got our imaginary sprite here, but if our sprite is entirely off the top of the screen, or the bottom of the screen for that matter, we're not going to draw anything. Save ourselves some time. Okay, so let's have a look at this doCrop routine and let's see how that works. Now, if you've seen the other examples of this code, it's basically the same each time, just with a few tweaks. So here is the start of our code. We load the Y register with a 0. Y maintains a value of 0 at all times, so you'll see it being used to clear entries at various points. Now, the first one we're zeroing is sprite hclip. Now, sprite hclip is used for the cases when our sprite is either partially off the left-hand side of the screen or partially off the right hand side of the screen, and this is used for storing the number of tiles in this case that we need to skip in our source before the next line. So that's what that's going to be used for. D and D are just some temporary variables that we use during our processing. So first what we're going to do is we're going to load in the Y position of our graphic, and what we're going to do is we're going to subtract the first logical vertical unit of the visible screen, and what this is effectively going to do is it's going to take our sprite and it's going to move it up, and it's going to see if the sprite, for example, is partially off the screen here. If it is, then our Y position would effectively be negative at this point, and we're going to have to work out how much we need to crop to get to the first visible tile that we need to draw on the screen. So first of all, we're just branching here if we've not got anything we need to crop, but if we have, we're converting that negative back to a positive. We're then masking it out to a total number of tiles because our logical units are in pairs of pixels, but we need to work it into a multiple of 4 logical units so that we've got a count of tiles that we can work with. So that's what we're doing there. We're then comparing it to the height of the sprite, and if what we're actually doing here is skipping the entire sprite, then the graphic must be entirely off the screen. So we're branching to this all off screen function here, and all that does is it sets the carry and returns because there's nothing on the screen to draw. Now, if we get to here though, then there is something to draw, but something needs removing. So we're storing the amount to remove from the top in the 0 page entry E, and we're then setting the C position, that's the vertical start, to 0, transferring it from Y here. This is the new position that we're going to want to start to draw our graphic in. Now, this is still in logical units, but we will convert it to tiles later on. Okay, so we've looked at cropping the sprite at the top of the screen. We're going to now do the same for the bottom of the screen. So we're adding the height of the sprite, and now what we're doing is we're comparing this to the logical height of the logical screen. And we're going to see if this is overflowed, and if it is, then we must be over the bottom of the screen. So maybe our character is somewhere like this, and so maybe part of the bottom of the sprite needs to be cropped. Well, that's what we're going to do here, but first again we're converting this to a number of tiles, seeing if there's anything left not being cropped, and we're storing the amount to remove from the bottom in ZD. Okay, so we've now got the amount to remove from the top in E, the amount to remove from the bottom in D. We're adding those together and seeing if anything needs to be being removed from the top or the bottom. And if it does, we're subtracting that from the old height and updating the new height of the tile graphic that we need to draw to the screen. Now we're going to convert that to a number of tiles later on, but what we're going to do next is we're going to see if we need to remove anything from the top of the graphic. So what we're doing here is we're converting our number of logical units that we need to remove from the top of the graphic into a number of tiles that we need to remove from the top of the graphic. And then what we're doing here is we're calculating the number of tiles in each line by taking the width and shifting it to the right twice, and this calculates the number of tiles in the width of the graphic that we're showing to the screen using the tile map. We're then adding this count multiplied by the number of lines we need to remove from the IY pair here. Now this is effectively the source tile number, because if our graphic is off the top of the screen, well, this first part on the left here will need to be removed if we're up somewhere like that. So that's what we're doing here. We're removing part of the graphic, and we've got a very crude multiplication routine here that repeatedly adds ZE to the HL pair here, which will remove them from the top. Now, that's not a very efficient routine, but this is only going to be run once per draw and only when the sprite is partially off the top of the screen. It's a very infrequent occurrence, so I'm not particularly worried about performance here. Okay, we've done the top. We're now going to do the same for the left and the right here. So we're zeroing the D and E pair because those are just temporary variables. We are done with them for the top and the bottom. And we're now going to do the same with the left and the right. We load in the X position. We subtract the first logical X position that is visible, and we're seeing if we are off the left hand side of the screen. You know, maybe our graphic is somewhere like this and we need to remove part of the sprite. So that's what we're doing here. We're seeing if we are needing to remove the entire width of the sprite, and if not, we're storing the amount we do need to remove in ZE. We're setting the new X position to 0. We're storing the new X position there. And now what we're going to do is we're going to do the right hand side. So we're adding the width of the sprite, we're comparing that to the width of the logical screen, and we're seeing if anything needs cropping. So we're seeing if our sprite is somewhere like this and we need to remove part of it from the right hand side of the screen. Again, we're seeing if we are needing to remove the entire width of the sprite, and if not, we're storing the amount to remove in ZD. So once again, ZD is now the amount to remove from the right, ZE is the amount to remove from the left, and we are now going to convert those to a number of logical tiles and see if there's anything we need to remove. We're shifting to the right twice, effectively dividing by 4, because as I say, there's 4 logical units per tile. And if there is an amount we need to remove, we're storing that in sprite hclip, which is the amount of tiles we need to remove from the side of our sprite after each draw. Okay. So what we're going to do now is we're going to convert that back to a number of tiles, and we're going to add that to the width of our graphic, and we're going to store that back to the new width in logical units. Now, the next thing we're going to do is we're going to see if we need to remove anything from the left-hand side of the graphic, because again, just like with the top, if we're off the far left, we need to skip something before we even start drawing. And that's what we're doing here. So we're taking E, converting that into a number of logical tiles, and we're adding that to the first drawn tile here. Okay, we've now calculated all of our cropping. The last thing we're doing here is we're converting all of our logical units into a number of tiles here. So we're effectively quartering the X pos, the Y pos, the width and the height here. This now converts them all into a number of tiles, and we're going to use that during our draw routine. But before we discuss our draw routine, we're going to discuss the non-maskable interrupt handler, which is transferring our tile changes to the tile map during VBlank. Okay, let's take a look. Now, you will notice that during our code, we are actually defining some variables here. We're defining a VDP buffer address here at memory address 200, and we're defining a VDP count, which is the number of tiles we need to transfer during the next VBlank. So we're going to see those during our NMI handler here. Now, what our NMI handler does is it transfers all of our tiles. Now at the start we've got some code that handles the sprites, but we don't need that for this time. But what we do need to do is we need to transfer the count of the number of tiles we need to change from the VDP buffer. Now the count is actually the number of bytes to transfer, and for each tile that we're changing in the format I'm using, we're using 3 bytes in total. The first one is the high memory address of the byte we want to change. The one afterwards is the low memory address of the byte we want to change in VRAM. And the third one is the new byte for that address in VRAM. Now, this isn't that efficient. You could do something like RLE compression, but for the purposes of today's example, this is good enough, and it allows us to transfer a total of 32 bytes within the time the VBlank takes. Any more than that, and VBlank would probably end on us. So that's what we're doing here. So we are setting the memory address with 2 writes to 2006, and then we're setting the new value for that address in 2007. So all we need to do is we need to transfer the 3 bytes, the address and the new data byte, to VDP buffer, and make sure VDP count is updated correctly for the VBlank to handle it. We of course also need to make sure VBlank count doesn't go over 32 times 3, because we can only transfer 32 different tiles per interrupt, and there are 3 bytes per tile. So we're going to see that as well during our sprite routine. Okay, so we did our do crop before, and if the carry is set, we're just going to return. Otherwise, we're going to draw our tilemap graphic to the screen. Okay, so here's the start of that routine. So we're loading X with the width in tiles now, and we are loading the accumulator with the X position here, and we're going to do that because we're going to need to restore it later on. Now what we're doing here is we're using a function called getVDPScreenPos. This will calculate the VRAM destination of the tile we want to change, and it will also set up the Y register to point to the next memory address within the buffer that is going to be the new tile number. So that's doing most of the work for us, and we'll have a look at it in a moment. What we're then doing is we're loading the new tile number and writing it to the next position in the buffer. We are then increasing the buffer count, and we are storing that new buffer count in VDPCT here. We're also increasing the new tile number that we are showing, and we're repeating that for the entire width of our tile map here. So that's transferring that Chibiko graphic to the screen. That will have done one strip of the Chibiko graphic. After the end of that though, we need to move down a line, and that's what we're doing here. We're moving down a line with C, which is the Y line. We're then adding, if needed, any skipped tiles from the position from the sprite. As I said before, if our sprite is on the left or the right, we need to remove a few tiles before we start drawing the next line of that graphic. So that's what we're doing here. So we're removing those just there, and then we're repeating until the entire line of the graphic is done, and that is effectively all that it takes to do our graphic. Now, as I say, this is the code that's handling the drawing of the Chibiko graphic, as you can see it here, and it's also handling the cropping when the graphic goes partially off the screen. As I say though, a lot of the dirty work is being done by this getVDPScreenPos function, so let's take a quick look at that. Okay, so here it is. This is the function itself, and what we're doing here is we're effectively taking the Y position here, and we're converting this and the X position from a X and Y position in tiles to a memory address within the tile map, and the tile map is in memory address 2000 onwards in VRAM. We're calculating that memory address in the H and L pair here, and so the address is effectively 32 times the Y pos plus the X pos. That's what all of these bit shifts is doing here. And then what we're doing here is we're writing the H and L pair into the VDP buffer here, and then we're returning with Y set to the next position in that VDP buffer, which we then write our tile number into. Now we've got this getVDP buffer function here, which is getting the next position within VDPCT, which is the offset within that buffer. But first we're checking if the offset has already reached 32 times 3, because if it has, then that's the limit of the number of tiles we can successfully transfer within one VBlank. And so if we've done that, we're then waiting for the next VBlank, which is why the screen's flickering sometimes. So that's what's going on there. As I say, this is effectively doing all of the calculation of the destination VRAM address, and it's also calculating the next position within the buffer and waiting, if necessary, for the VBlank for the buffer to clear. So that's doing all of that dirty work for us, and that's what allows us to get our tilemap onto the screen. Now, that's the end of today's episode. If you've liked what you've seen, please like and subscribe. As always, you can go to my website, download today's example, and do whatever you want with it. If you manage to make some kind of amazing use for it, good luck with it. You're welcome to use my code in any way you want. Hopefully you're going to like and subscribe though, because next time we're going to be looking at a better version of today's example. We've been using the tilemap today, which gives us clunky, nasty, slow movements of our graphic. Next time we're going to be looking at using hardware sprites, which is, it's not necessarily trickier, it puts in more limitations because we can only have a limited number of sprites on the screen. But we'll be seeing that next time, so hopefully you'll stick around for that. Anyway, hope you've enjoyed what you've seen today. Thanks for watching today, and goodbye.